In this video, we're going to talk about inverse matrices. So just like a number, say 2, has an inverse, 1/2, some matrices also have an inverse matrix. So we want to figure out how to determine which ones do and how to find them. But before we do that, there's a very special set of matrices called identity matrices that we need to talk about. So the identity matrix of size n is a square matrix, so it's size n by n, and it has 1s along the main diagonal, 0s everywhere else. Okay, we denote these with I sub n, okay, because there's 1 for every positive integer size n. So for example, okay, I1 is just the 1 by 1 matrix with the number 1 in it. I2 is a 2 by 2 matrix, 1s along the main diagonal, 0s everywhere else. I3 is going to be a 3 by 3 matrix, and it's going to have 1s along the main diagonal and 0s everywhere else. Okay, so the main diagonal is from the top left to the bottom right, 0s everywhere else. This looks like the diagonal form that we were trying to achieve when we were row reducing. Okay, they have the same form as that. But here they're just a single matrix. Okay, these are called the identity matrices. So what's special about these matrices? So let's try to compute the identity matrix of size 2 times this 2 by 2 matrix. So what the I2 looks like 1, 0, 0, 1. And then we want to multiply it by this matrix 1, 2, 3, 4. Okay, so notice that they're both 2 by 2 matrices. So the matrix operation multiplication is defined because these two numbers are the same. And we're going to get a 2 by 2 matrix. Okay, so I'm going to perform this multiplication so that hopefully you believe me what's going on here. So we take this row times this column. That gives us the first entry here. So it's 1 times 1 plus 0 times 3. And then we take the first row times the second column. That gives us the entry in the first row, second column. So 1 times 2 plus 0 times 4. Okay, now I want to do the same thing with the second row. So this row times the first column gives us this entry here. So it's 0 times 1 plus 1 times 3. Okay, and then the last one, second row, second column, gives us the entry in row 2, column 2. And it's 0 times 2 plus 1 times 4. Okay, so now if I simplify, this is 1 plus 0, and then 2 plus 0. And then it's going to be 0 plus 3, and then 0 plus 4. So what I get is 1, 2, 3, 4. Now notice, I'm running out of highlighter colors here. Let's do pink. Notice that this matrix here is the same as the matrix we started with. So that's not a coincidence. Okay, this is what's special about these identity matrices. So when you multiply by the identity, nothing happens. So it doesn't change the matrix. This is like multiplying by the number 1. Okay, so when we're using real numbers, if you multiply by 1, nothing happens. So the identity matrices are like the 1s for matrices. Okay, so assuming that the multiplication is defined, and you can always make it defined by just choosing the appropriate identity matrix, it doesn't do anything. Okay, so how does this relate to the inverse? Well, like numbers, 2 times its inverse, which is 1/2, gives us a 1. So we want the same idea for matrices. So if I have a square matrix A, then its inverse, which we denote A to the minus 1, is the square matrix A inverse, is what we call this. So let me just write that. So when you read this, you say A inverse. It's the matrix A inverse so that when I multiply the two matrices together, I get the identity matrix, okay, of some size. Okay, so the identity matrix is going to be the same size as A and A inverse. So let's just verify that these two matrices here have inverse, they're inverses of each other. So if we wanted to verify that, what I want to do is multiply them together. Okay, so I'm going to take these two and multiply them together to see if I get the identity matrix. Technically, I should do it on both sides, but it's going to be the same. So if I take row 1 times column 1, it's going to be 2 times negative 1 plus 1 times 3. Row 1 times column 2, 2 times negative 2 plus 1 times 4. And then I'm going to have negative 3 over 2 times negative 1 plus negative 1/2 times 3. And then I'm going to have negative 3 over 2 times negative 2 plus negative 1/2 times 4. Okay, now if I simplify this, this is negative 2 plus 3. And then I have negative 4 plus 4. Down here I have 3 over 2 minus 3 over 2. And then I have 3 minus 1/2 times 4 is 2. Okay, so simplifying here, I get 1, 0, 0, 1. So I get the identity matrix of size 2. Okay, if you check the other way, which I encourage you to do, you'll also get the identity matrix of size 2. So in fact, these two matrices are inverses of each other. Now, do all matrices have inverses? It might be something you're thinking about. So notice that it was only defined for square matrices. Okay, so first of all, the matrix has to be square. So the answer to this is no. Okay, so the matrix only hope is when the matrices are square. So that means if you're not a square matrix, there's no hope of you having an inverse. Okay, so it must be a square matrix. But it turns out that even when they are square, sometimes they don't have inverses. Okay, so even some square matrices do not have inverses. Okay, so we want to be careful. It's special to have an inverse in the land of matrices. So let's try and find a matrix inverse. So we're going to use the definition. So let's just so we don't know what the inverse is going to be, okay, but we know it's going to be the same size as A. So let's call it X, Y, Z, W. Okay, it's going to be a 2 by 2 matrix. Now in this example, I'm going to go through straight through how to find an inverse, but there's actually going to be a shortcut method from this that we're going to hopefully see. Okay, so you won't have to go through this whole procedure every time. So in order for this to be an inverse, okay, we must have that A times A inverse is going to be I2, because they're 2 by 2s. So what that means is that the matrix 4, 5, 2, 3 times this matrix X, Y, Z, W should give me the identity matrix like that. Okay, so if we simplify the multiplication, I'm going to row 1 times column 1 is going to be 4x plus 5z. Row 1 times column 2 is going to be 4y plus 5w. Row 2 times column 1 is going to be 2x plus 3z. And then I'm going to have 2y plus 3w. And that should be equal to this identity matrix. Okay, so what that's going to give us is it's going to give us a system of equations. Okay, so let's get some colors out here. So this 4x plus 5z has to be equal to 1. Okay, so that's going to be an equation that we have up here. So we need 4x plus 5z to equal 1. So we also need 2x plus 3z to equal 0. Okay, so 2x plus 3z should equal 0. We should have 4y plus 5w equal to 0. And we should have 2y plus 3w equal to 1. So we get these four equations. Now, if we were going to solve this, and we wanted to use, say, Gauss-Jordan elimination, there's 4 variables and 4 equations, okay? So you can do it, but it's going to be a big, big system, okay? So what we want to notice is that these first 2 equations only use x and z, and these second 2 equations only use y, and w. So we can actually solve them separately because they don't depend on each other. Okay, so we can solve them separately. So to solve the xz ones, we'd want to row reduce, or you could use other methods, okay, but I'm going to talk about row reduce. So you'd row reduce a matrix that looks like 4, 5, so I'm doing an augmented matrix here, 4, 5, the line, and then 1, 2, 3, the line, and then 0, okay? For the YW system, you'd want to row reduce the augmented matrix that looks like 4, 5, and then a 0, 2, 3, and then a 1. What do you notice about these 2 systems? Well, they have the same coefficient side. Okay, so that's this side here. Okay, so the augmented side or the constant sides are different, but the coefficient sides are the same. So what that means is they're going to use the same row operations to solve both. So we could solve them at the same time. Because to do the first one, we're going to be using the sum row operations, and we're going to use them on the column 1, 0. On the YW one, we're going to do the exact same row operations, but we want to do them on the column 0, 1. So what we're just going to do is row reduce just a bigger augmented matrix. So 4, 5, 2, 3 on one side, and then I'm going to have the 1, 0 column, and also the 0, 1 column. Okay, so this column is going to be the xz for xz, and this column over here is going to be for the yws. So when we're solving for those. So at the end, we're going to have to remember that we actually solve 2 different systems here. But we're going to row reduce just like normal. Okay, the rows are just a little bit bigger. So my first step, I'd want to pivot around this first entry. So I'm going to do row 1 divided by 4. Okay, and I have to divide the whole row by 4. So I'm going to get 1, 5 over 4, 1 over 4, and then a 0. Row 2 didn't change. Okay, now I'm still pivoting around this number. So I want to do row 2 minus 2 of row 1. Okay, so now I'm only changing row 2. Oops, doesn't look right. Okay, I'm only changing row 2, so this is going to be a 0. In this entry, I'm going to have 3 minus 2 times 5 over 4. So that's actually 3 minus 5 over 2. So it's 6 over 2 minus 5 over 2. I think I get 1 over 2. Okay, now I'm going to have 0 minus 2 times 1 over 4. That's just going to be minus 1 over 2. And the 1 minus 0 is still 1. Okay, now I want to pivot around this entry. So I could divide by 1/2 or multiply by 2 on row 2. Okay, so this is going to be 0, 1, this is going to be -1, and this is going to be 2 when I multiply by 2 everywhere. Still pivoting here. So my last step is to make that 5 over 4 a 0. So I do row 1 minus 5 over 4 of row 2. Okay, so now I'm going to have the diagonal form on the left side. Okay, and then on the up here, so in this entry, I used to have 1 over 4, but I subtracted 5 over 4 times minus 1. Okay, so that's 1 over 4 plus 5 over 4 is actually 6 over 4, which is 3 over 2. Okay, and then in the last spot, I used to have a 0. Now I'm subtracting 5 over 4 times 2. So that's going to be just -5 over 2. Okay, so we're done row reducing. Now we want to remember what were we actually doing? We were solving two different systems here. So what I actually had is a system that looks like 1, 0, 0, 1, and then 3 over 2 and -1. Okay, that's my XZ system because that was the first column. Okay, and I had another system with the diagonal form on this side and the -5 over 2 and 2 on that column. That was my YW system. Okay, so then what that tells me, remember we have to go back up here. So my columns here were X, Z, and Y, W. Okay, so my answers here, I get, so from the first one, I get X equals 3 over 2, and Z equals -1. And from the other one, I get Y equals -5 over 2, and W equals 2. So now we figured out what are the entries in A inverse. So remember A inverse was X, Y, Z, W. Now I know that this is 3 over 2, -5 over 2, -1, and 2. Where have I seen that before? Okay, notice this matrix here is what we ended with on this side. So this is actually our sort of shortcut method. So we can ignore all the X, Y, Z, W's type thing. What we actually did was we put the matrix that we wanted to find the inverse of. Okay, so notice that that was A here. So after all of that work, the thing that we actually wanted to row reduce in both had coefficient matrix A. And then we augmented it with the identity of the same size. Okay, we do our row reduction, and we end up with the identity on the left, and then the matrix on the right is the inverse. Okay, so that's going to be our shortened method. We still need to do the Gauss-Jordan method elimination though. So, given an n by n matrix A, so a square matrix, we can determine A inverse, okay, if it exists, because remember, not all square matrices have an inverse. So what we do is we augment A on the left, so matrix A, and the identity matrix of the same size, so IN, on the right. Okay, so that's going to look like A with a line and then I sub n. Okay, and then we're going to row reduce this matrix to get the identity on the left. Okay, and then whatever's on the right is going to be your inverse. Okay, now if you cannot, so remember when we were solving systems, it wasn't always possible to get diagonal form. So if you cannot row reduce to get the identity on the left, so diagonal form, then your inverse doesn't exist. Okay. Now, if you have a 2 by 2 matrix, there's a nice formula you can use. This is proved by just doing this procedure for a general matrix A. Okay. But if you want to use this formula, you're welcome to for 2 by 2s. So if you have a 2 by 2 matrix A here with A, B, C, D, then your inverse is going to be 1 over capital D, and then the matrix D, negative B, negative C, A. Okay, and your capital D is this AD minus BC. Okay, and it can't be 0 because we're dividing by it, so we don't want it to be 0. So if you want to use this formula, the idea, or how you can remember what to do, okay, is you switch the A and D entries. Okay, so you switch their spots. You negate the B and C entries. Okay, but leave them in the same spots. Okay, and then you divide everything by capital D is AD minus BC, okay, which obviously can't be 0. So the ones you want to switch are the ones on the main diagonal. Okay, and the ones you just negate, we call this the off diagonal. Okay, so it's the other diagonal. You negate those. So let's just do a couple of examples. Okay, so here's a 2 by 2 example. Let's just use the formula first, even though it says to do Gauss-Jordan method. So if I use the formula, let's compute D first. So it's going to be 2 times 3 minus 4 times 2. Okay, so you multiply and then subtract those multiplied. Okay, so this is 6 minus 8, which is minus 2. So it's not 0, that's good. So then A inverse is going to be 1 over negative 2. Okay, so now I switch these two. So the 3's up here, the 2's down here, and then I just negate the other 2. But they stay in their same spots. Okay, now I want to divide everything by negative 2. So I get negative 3 over 2, a 1, a 2, and a negative 1. Okay, so that's my inverse. Now let's try and do it with the Gauss-Jordan method. Okay, so what I want to do is I want to augment matrix A with the identity of the same size. Okay, so here that's I2. And now I want to row reduce. So I'm going to start in the top left corner. I want to do row 1 over 2. So divide everything by 2 in row 1. So I'm going to have 1, 1, 1/2, 0. And then I want to make that 4 a 0, so I'm going to do row 2 minus 4 of row 1. So row 1 is not changing. Oops. So this one's going to be a 0. Now I'm going to have 3 minus 4 is minus 1. 0 minus 4 times 1/2 is minus 2. And 1 minus 0 is just 1. So now we negate row 2, because I want to make that negative 1 into a positive 1. So 0, 1, 2, negative 1. And then last step is I want to make that 1 a 0. So row 1 minus row 2. 0, 0, 1. So now I have the identity on that side. And I'm going to have 1/2 minus 2 is negative 3/2. 0 minus negative 1 is a positive 1. So now I see that I have I2 here, which means that this part is the inverse. So I want to write A inverse is equal to the 2 by 2 matrix, negative 3 over 2, 1, 2, negative 1. And notice that that is the matrix we got here is exactly the same as the matrix we got here. Okay, so it's the same answer, just different method. Okay, one more. So we want to find the inverse of this 3 by 3 matrix. Now, because our matrix is a 3 by 3, we cannot use the formula. Okay, you can only use the Gauss-Jordan method. That's the only way we know. So I'd want to augment the A matrix with the identity of the same size. So that here is going to be I3 this time. Okay, so I have A, and then I have I3. So we are going to start in the top left corner. It's already a 1, so I have to do row 3 minus row 1. So row 1 and row 2 are not changing. Okay, now row 3 is going to be a 0. 5 minus 3 is a 2. 10 minus 2 is an 8. 0 minus 1 is negative 1. 0 and a 1. So I move down 1 over 1 and pivoting around that 1. So I'm going to do row 1 minus 3 of row 2. Okay, so this is now going to be a 0. 2 minus 3 times 4, so that's going to be a minus 10. 1 minus 0 is still 1. 0 minus 3 times 1 is minus 3. And that one's going to be a 0. Now I'm also going to do row 3. So it's row 3 minus 2 of row 2. So now this spot's going to be a 0. Okay, now 8 minus 2 times 4 is 8 minus 8, which is a 0. Negative 1 minus 0 is negative 1. 0 minus 2 is negative 2. 1 minus 0 is 1. So my next step would be to pivot around this 0. Okay, now I can't pivot here. I can't switch. This is where the row reduction would stop. Okay, so notice that we were unable to get I3 on the left. Okay, so what that means here is that A inverse for this matrix A does not exist. So because we were not able to row reduce to get diagonal form on the left, or the identity, we can conclude that the inverse does not exist.